Hello, I'm VPK Vijayaraman. I'm going to show a presentation on the speed control of the induction motor drives. Induction motor drives. Before discussing about the induction motor drives, it is important to understand and know about the induction motors. It is in very simple words, induction motors can be described as a three-phase self-starting constant speed AC motor. The reason for describing induction motor as a constant speed because normally these motor have a constant speed depending on the frequency of the supply and the number of the windings. An induction motor or a synchronous motor is an AC electric motor in which the electric current in the rotor is needed to produce torque is obtained by electromagnetic induction from the magnetic field of the stator winding. Rotating electric machine must possess stator and the rotor, and there should be air gap between this and a mechanical interconnection through the shaft and bearing. Starting method for induction motor. Why we need a starter for this? At the starting, the three-phase induction motor behaves like a transformer with short-circuited secondary. In that condition, while applying a rated voltage, the starting current will be maximum or high. Starters are intended to limit the high starting current. Types of starter. Based on the types of the rotor of the induction motor, there is two types: squirrel cage induction motor and wound rotor induction motor. In a squirrel cage induction motor, direct online starter, stator resistance starter, auto transformer starter and star delta starter are used. In a wound rotor induction motor, rotor resistance starter is used. Rotor resistance control of the induction motor. The conventional method for variation of the rotor resistance was done by inserting a variable rheostat in series with the three-phase winding of the motor. This method of speed control faced problems and this is not economically viable. The variation of the rotor can be done by using power electronic devices and this is more efficient method. The torque equation of a polyphase induction motor is given. Under normally working condition, R2 by S is very greater than R1 and X1. Therefore, the equation means S is equal to T by KT into R2. This equation shows that the constant torque, the slip is directly proportional to the rotor resistance. If the resistance in the rotor circuit is increased, the slip is increased and the speed of the rotor is decreased. This method is applicable only to the wounded induction motor. From this graph, we can clearly know the speed is varying with the change of rotor resistance. At the normal operating condition, the slip increases with the increasing torque. Hence, they are obeying a linear characteristics. For a fixed load curve, the speed is downward from N1 to N4. From this, we can obtain the maximum torque of the starting of the resistance R2. So, this method has an advantage of achieving maximum torque at the starting period. But the maximum torque is independent of the rotor resistance as per the equation torque max. And drawbacks. The rheostat which is used to vary the resistance per phase causes unbalancing in rotor. The resistance generate huge loss and generate heat in the system. In case of the large machine, the size of the rheostat will be large and in such case it is not easily portable. Next, advantages of the speed control of induction motor using static devices. Smooth variations of the rotor resistance. Simplicity of operation using closed loop control. Using this, the response of the system is very quick. Rotor resistance unbalanced can be eliminated using power electronic devices. Slip power recovery scheme used in induction motor. Motor which is fed electrical supply from both stator and rotor is called doubly fed induction motor. When a power crosses from stator to rotor, there is a air gap power. It crosses a small rotor copper loss here. So the equation of the remaining power will be mechanical power, and the mechanical power is PM is equal to Pg minus PR, where PR is the power absorbed by the source VR. The magnitude and the sign of the PR can be controlled by the magnitude and the phase of PR. When PR is 0, the motor runs its natural speed torque characteristics. A positive PR will reduce the PM and therefore motor will run at a lower speed for the same torque. When PR is made equal to PG, then PM and consequently speed will be 0. Thus variation of the PR from 0 to PG will allow speed control from synchronous to 0 speed. Polarity of the VR of this operation is a continuous line. In a simple, the excess kinetic while controlling induction motor, while controlling a speed control of the induction motor, there will be excess of kinetic energy, and this kinetic energy will be wasted. For this can be recovered and fed back to the AC source. Since the excess kinetic energy can be converted into electric energy at the rotor side and fed back to the source, this method is called slip power recovery. This slip power recovery can be possible only while the speed is to reduced or the motor is to be braked. Static ski bus drive. In the circuit we have a inductor. This is a smoothing inductor, and this thyristors works as a line commutated inverter. The line commutated the thyristor works like a line commutated inverter by changing the firing angle of the DC firing angle. DC is converted into AC and fed back to the source through the transformer. Here the thyristor works like a light commutated inverter, and it gives a supply to the and fed back the kinetic energy to the source by this transformer. This is the working of the static ski bus drive. This type of recovery is slip recovery because in addition this is called static device because in addition to the motor there is no rotating item. Excess kinetic energy can be converted into DC by the rectifier, and this rectified DC is converted into AC by the line commutated inverter. Transformer used to match the voltage of the inverter to grid and feed back this energy. And induction is used to smooth out rectified DC. Amount of power fed is controlled by the firing angle of the inverter. It is possible only the speed is being reduced and the motor has excess kinetic energy. Reactive power is still consumed from the source, and the power factor is poor in this. Since slip power recovery scheme is used in induction motor is fed back to the source, unlike rotor resistance where it is wasted in resistance. Drive has a less efficiency. The drive has a higher efficiency than the stator voltage controlled by the AC voltage controllers because of the same reasons. Drive input power is the difference between the motor input power and the power feedback. Reactive power is the sum of the motor and the inverter reactive powers. Therefore, drive has a poor factor through the region of its operation. Next, static Kramer drive. In static Kramer drive, this separately excited DC motor and the induction motor are connected through a same shaft, and this is separately excited DC motor has a field control. Hence these two motors is connected to the same shaft, so both can run the shaft. When you want to reduce the speed, there will be a more kinetic energy. There should be more kinetic energy. This diode rectifier gives DC to the separately excited DC motor. Due to this, motor produce a torque since two motor mounted on the same shaft. Induction motor will produce a less torque, so whatever energy produced in the induction motor will be reduced. Indirectly, we can reduce the power. And also the control by controlling the DC motor, the speed can also be reduced. Rotor slip is converted into DC by the diode drift. The diode power is now fed to the DC mechanically coupled induction motor. Torque is supplied is sum of the torque produced by the induction and DC motor. Speed control is obtained by controlling field current of the DC motor. The variation of VD1 and VD2 with speed for two values of DC motor field current. The steady state operation is obtained when Vd1 is equal to Vd2 at A and B for field currents. If